Today I'm going to be talking about this important article, Neural Collapse Inspired Feature Classifier Alignment for Future-class Incremental Learning. This paper in 2023. Future-class incremental learning has been a challenging problem as only a few training samples are accessible for each novel class in the new sessions. Fine-tuning the backbone or adjusting the classifier or prototypes trained in the prior sessions would be inevitably cause misalignment between the feature and classifier of old classes, which explains the well-known catastrophic forgetting problem. In this paper, we deal with the misalignment dilemma in FSCIL, inspired by a recently discovered phenomenon named as neural collapse, which reveals that the last layer features of the same class will collapse into a vertex, and the vertices of all classes are aligned with the classifier prototypes, which are formed as a simplex equiangular tight frame. It corresponds to an optimal geometric structure for classification due to the maximized Fisher discriminant ratio. We propose a neural collapse inspired framework for FSCIL. A group of classifier prototypes are pre-assigned as a simplex ETF for the whole label space, including the base session and all incremental sessions. During training, the classifier prototypes are not learnable, and we adopt a novel loss function that drives the features into their corresponding prototypes. Theoretical analysis, my last 3 slides, show that our method holds the neural collapse optimality and does not break the feature classifier alignment in an incremental fashion. There are 2 major contributions in this paper. First one is that we want to relieve the misalignment dilemma in FSCIL. So they propose in this paper to pre-assign an optimal alignment inspired by neural collapse as a fixed. So this pre-assigning is a very smart action that they are doing, inspired by neural collapse as a fixed target throughout the incremental learning. So our model is trained towards the same optimality to avoid optimization conflict among sessions. We fix the prototype and apply a novel loss function that only fine-tunes a projection layer to drive the output features into their corresponding prototypes. Theoretical and empirical analysis show that our method better holds the neural collapse optimality. So this is a popular choice in prior studies to evolve the old class prototypes by delicate designs of loss or regularizer to keep them separated from novel class prototypes. So prior studies show that classifier prototypes are learnable, but in this paper, classifier are pre-assigned and fixed. Those prototypes, we fix them, we don't learn them. So in real-world applications, one often needs to adapt a model to a data coming from a new label space with only a few labeled samples. But FSCIL trains a model incrementally on a sequence of training datasets, and D0 is the base session, and T is a number of incremental sessions. So the base session usually contains a large base space and sufficient training images for class C. And in each incremental session, there are only a few labeled images. And so neural collapse refers to the phenomenon that at the terminal phase of training, and it reveals a geometric structure formed by the last layer feature and classifier that can be defined as so we define simplex equiangular tight frame, which we need. A simplex equiangular tight frame, or we call it ETF for short, refers to a matrix. So this one is a matrix composed of k vectors in Rd, and E allows a rotation and satisfies this property where this I is the identity, and all columns vector have the same L2 norm, and any pair has an inner product of -1 over k minus 1. So we want to create a fixed frame, and the last layer feature of the same class will collapse into within class mean. So the covariance converges to 0, and mu is the feature of the sample I in class K, and mu K is the within class mean of class K features. Neural collapse 2. The within class means of all classes centered by the global mean will converge to vertices of a simplex ETF. And neural collapse 3. The within class means centered by the global mean will be aligned with their corresponding classifier weights, which means the classifier weights will converge to the same simplex ETF. And neural collapse 4, when neural collapse 1 and 2 hold, the model prediction using logics can be simplified to the nearest class centers. Assume that the base session contains a label space of K0 classes. Each incremental session has P classes, and we have T incremental sessions in total. The whole labeled space has K0 here, and then K prime classes, so we have TP more, so the overall is K0 plus K prime. A popular choice in the current studies learns F. This is our backbone networks using the base session data. In incremental sessions, F is fixed as a feature extractor, and only this matrix for novel classes is learnable. Since neural collapse describes an optimal geometric structure of the last layer feature and classifier, we pre-assign such an optimality by fixing a learnable classifier as the structure instructed by neural collapse. So we adopt an ETF classifier that initializes a classifier as a simplex ETF and fixes it during training. The difference lies in that we use it in an incremental fashion. Concretely, we randomly initialize classifier prototypes for the whole label space. The union of classes of all. So we are not training them, we just randomly initialize it and then we fix it. So we have a backbone network, and then we have projection layer, and then we get the weights. So this one is the ETF classifier that contains prototypes of the whole label space and serves as a fixed target throughout the incremental training. Here, H sub I is the intermediate feature from the backbone network, and mu sub I is the normalized output feature after the projection. The gradient of the cross-entropy loss with respect to the last layer feature is composed of a pull term that derives the feature into its classifier prototype of the same class, and a push term that pushes it away from prototypes of different classes. So when the classifier prototypes are fixed, the pull term is always accurate towards the solution, and we can drop the push gradient that may be inaccurate. So we adopt a novel loss name dot regression loss that can be written like this. The projection layer G can be a linear transformation or multi-layer perceptron block, and it projects the intermediate features into these mean. And then we perform L2 normalization and the mu I to get the output mu I hat. So here theta F and theta G are the parameters of the backbone network and the projection layer. So in the base session, we jointly train both F and G using the base session data. And the empirical risk to minimize the base session is this. And here is the pre-assigned ETF classifier. In each incremental session, we fix the backbone network as a feature extractor and only fine-tune the projection layer. As a widely adopted practice, a small memory of samples or features of all classes can be retained to relieve the overfitting on novel classes. The empirical risk to minimize in incremental sessions is this, where this one are the output features of X sub I and H sub C, and this is the number of training samples in session T. And because we have a pre-assignment alignment, so we don't need to rely on a regularizer. And these are the theoretical supports in the last slides. We perform theoretical work based on a simplified model that drops the backbone network and only keeps the last layer for simplicity for analysis. So this simplification has been widely adopted. So we consider this problem of this minimization problem, and M here, this denotes a feature variable that belongs to the I sample of class K, and sub K is the number of samples in class K. KT is the number of classes in session T, and NT is the number of samples in session T. So the theorem says that let M hat denote the global minimizer of that, and then when L is CE or the R loss for any column vector, then we have this dot product.